Okay, so in this video, we are going to learn about hybridization. What is hybridization and the need for hybridization. At the same time, we will look at few concepts which are important for your competitive exams. Okay, hybridization. So it's a purely a hypothetical concept. It has no experimental proof. So let's see what happens if there was no hybridization. Let's consider CH4. So carbon's valency is 1s2, 2s2, 2p2. You can just consider the valence electrons to be now in the excited state, the electrons jump from 2s2 to p, giving us a configuration like this. Now we will have 1s electrons of the hydrogen atoms right? If there was no concept of hybridization, it was assumed that the atomic orbitals overlapped, and you would get something like this, where the oneness of hydrogen approaches the 2s and 2p of carbon, forming bonds like this. Okay. So what would this result in? Let me bring up a picture. It would result in something like this. Okay. Where we have carbon and hydrogen bonding together like that. What's the problem here? Now, if you look closely, what we have is three 1s 2p bonds and one 1s 2s bonds, right? So the s orbital, we know that it is spherical, and the electron distribution is uniform. The s orbital also being closer to the nucleus compared to the p orbital has a different energy level to it compared to the p orbital. In s orbital, there is no directional behavior. When you take the p orbital, it has a dumbbell shape with electron densities towards the edges of the p orbital being more. So this p orbital has directional behavior associated with it, right? And it is comparatively higher in energy compared to the s orbital. Now, the bond between 1s to p is stronger compared to the 1s and 2s. This is because in case of the 1s and 2s bonding, it would look something like this. So this is 1s and 2s. So this region will have relatively a weaker overlapping. This is because of the uniform electron distribution within the s orbital. But when you take 2p and 1s, since the electron density is more towards the edges of the p orbital, the bonding is much more stronger. So what does it mean? It means one of the four bonds in CH4 is weak. That can be any of the bond, right? So what would happen if you stress the molecule? It would go from CH4 to CH3, then further decomposition will occur. But that's not how it occurs. So when you ignite CH4, you get carbon dioxide and water. There is no breaking of one bond more quickly than other three bonds. In fact, all three bonds have equal bond dissociation energy. That's the first problem. So this is a big hit for your atomic orbital overlapping theory. Now the second thing is, if we were to assume that atomic orbitals overlap, it would mean that the orbitals are approaching each other through one particular axis, which you call the principal axis, which is usually the z-axis. So in this case, you see this atom, carbon, the hydrogens travel along the z-axis, the principal axis by convention, and the bond angle should be 90 degrees. Simple if I draw a line like this, you see that the bond angle is 90 degrees, which is also not true. The bond angle is 109 degrees. Okay. In order to explain these two faults, we introduce the concept of hybridization. So what does hybridization entitle? I told you that we have directional behavior in p orbital and comparatively high energy. That's the properties of the p orbital. Now the s orbital has less energy and non-directional behavior. That is the property of s orbitals. So what we are going to do is, we are going to bring both of them together and make a new orbital which has both directional behavior as well as a limited trade-off in terms of energy. There's a comparatively lower energy compared to the p orbital, right? Now let's see the p orbitals, 2p, directional behavior plus comparatively high energy, and the s orbitals, 2s, non-directional behavior plus less energy. So they combine to give us four new orbitals, 3 plus 1, 4 new orbitals, right? That is s plus p plus p plus p sp3. Okay, so all these orbitals are equal. So the bond dissociation energy of any one of the carbon hydrogen bond is same. Okay, in addition to this, what other things result as a consequence of hybridization is the bond angle. We can explain what exactly happens to the bond angle. Now, if I were to bring up an image of this orbital combining with the p orbital, you would know that the shape would change. Okay, so hybridization occurs from a spherical and a dumbbell shaped. You get what essentially is a irregular dumbbell where you have both directional behavior as well as relatively less energy. So this is the energy along the y-axis. So the s orbital is here, the p orbital is here, the hybrid orbitals are in between them. So this explains the bond dissociation fact. Now, if you look at this hybrid orbital, you can see that it is much more bulkier compared to the p orbital's dumbbell shape. This bulkiness is a consequence of increased S character, and we know that S character is directly proportional to the bond angle. Greater the S character, greater will be the bond angle. So why is that the case? Because S orbital will increase the electron density and it will look something like this. So there will be repulsion here and they will reach a position of minimum repulsion. That angle is 109 degrees. Okay. So this is why hybridization takes place, to explain these two phenomenons. So new hybrid orbitals formed, they are much more stronger than the bonds which are formed by the atomic orbital due to the thick electron density, right? And a very important thing that you have to keep in mind is hybrid orbitals never form pi bonds. They do not form pi bonds because they only have one overlapping zone. So no pi bond formation possible. For a pi bond to form, you need two overlapping zones, right? That's why whenever you see a pi bond and you're dealing with the second period elements, it's most probably unhybridized p orbitals, right? Now, let's talk about the hybridization index. Okay. So what is the hybridization index? Right. So hybridization index is represented by the letter I. So it is SPI. This part is the hybridization index. This part of the portion will help you understand things for the competitive exams. So I is the ratio of P and S. Okay. So the most important formula that you have to remember is cos theta is equal to minus 1 by I. So in your exams, if you were to have only the value of theta being the bond angle, you can find out the type of hybridization. For example, carbon dioxide, okay, CO2. I tell you the bond angle is 180 degrees Celsius. So cos 180 to minus 1 by 8 will imply that I is equal to minus 1 by cos 180 minus 1 by minus 1, which is 1. That means SP1 or just SP, which is correct. So this is a usual trick. Now let me show you how to calculate hybridization when you don't have the time to draw the orbitals, promote the electron, hybridize the orbitals, and predict the hybridization. So let's take CH4. You know that it is sp3, right? So don't draw this like that, draw it like this. A much more accurate representation. So to find out the hybridization, all you have to do is count the sigma bonds and the lone pair. So 1, 2, 3, 4. That is S, P1, P2, P3, P3, which is correct. And here, let's say CO2, S, P. Don't count the pi bonds, just the sigma bonds and lone pair, and assign them S, P, P1, P2, P3. Okay, so you get the hybridization of the molecule. So this would be SP. Yes, it checks out. So that's how you will calculate hybridization. Okay.